so we had, okay, so we're going to be talking about non-prime powers in modular arithmetic. So where did we leave off? So over the last couple of weeks, we've been talking a lot about Fermat's theorem. So for a prime p, if a is not congruent to 0 mod p, then a to the p minus 1 is congruent to 1 mod p. So this is incredibly powerful, right? Because it allows us to take powers for really large numbers and do that as basically just a division exercise where you find the remainder, as well as finding square roots, or I mean roots in general in modular arithmetic. But now we're all mathematicians here, at least for the next 2.5 weeks, you're mathematicians. And so we have a couple of questions, right? One of those questions might be, how can we generalize this? Can we replace things? So for example, can we replace lists? Oh, sorry, I don't think you can actually see me. Hopefully that's slightly better. Okay, so can we replace P with a composite number N. Okay, so can we do that? And we know that we can't just do that, because if we just do that, then things don't work out, right? Because sometimes you end up getting, well, powers that are equal to 0, or you end up getting powers that never equal to 1. So we also would probably need to replace this. So what conditions do we need on A? And of course, if you're going to replace P, then you also need to replace P minus 1. So what should we replace P minus 1? What should P minus 1? And lastly, the general goal is basically, is there some power? Can we get a power of A congruent to 1? Now, of course, I wouldn't be asking these questions in this class, at least, if the answer were no. So there is some way of generalizing this. And we're going to try to discover what that way is today. Now, there are a number of ways of going about this. And so, like I said last time, whenever you're trying to come up with a new mathematical theorem, there are several different ways. One is to do it by analogy. Another is to do it by just doing lots of experiments, so writing down lots of tables of things. And lastly, another way of doing it is to just like think really, really hard about the theorems. And so we're going to mix a combination of the last two ways today. So we're going to think hard about the theorems, but then we're also going to have an interactive, which is why I gave you the worksheet. And I'm going to give you a little bit of time to work on it, so you don't need to do it yet. But and then we're going to try to figure out what the natural generalization of Fermat's theorem to non-prime modulus ought to be. So of course, the basic question is, when can we get A to the T is congruent to 1 mod N, where N doesn't have to be prime? Well, if you think back to Fermat's little theorem, that was basically when you have the prime modulus, you notice that sometimes all of the Fermat's little theorem is basically sometimes the entire column is all ones, right? So, this is always true when N is a prime. But for composite N, that's not always true. Because when you're dealing with a composite number, sometimes you end up getting things that, like this here, from our prime powers interactive, you notice that sometimes you get things that are all zeros. Or sometimes you get things where you get repeated 2, 4, 2, 4, 2, 4, or sorry, 4, 8, 4, 8, 4, 8, but you never get 1 again. And so we know that this can't be true for composite numbers. And so then the question is, what can we say? Well, in the particular example we did in class a couple of weeks ago, we didn't actually fill out the entire table. Since we only did it for 1, 2, 3, 4, 5, 6, and we could, in theory, have filled it out for all the numbers mod 12. And so I'm not going to make you do that. So I did that, and this is what you get. So you fill it out for 0 through 11, the entire table. This is what you get. And you notice that things still don't seem that good, right? Because usually, so some numbers have a 1. So like there's a 1 here, 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 and here. But for many of these other rows, you don't have a 1 anywhere in them. So one thing that you might ask is, well, when do you get a 1? And this is a question that we've discussed a little bit. The answer is only when the greatest common divisor of A and N is equal to 1. Okay, and we can actually prove that. So this, if you were to do this experiment, you would notice these patterns. You do it for a bunch of numbers, and then of course you try to see, well, when do you get a 1 somewhere in the row? That's not just for the 0th power. And the answer is when the greatest common divisor is equal to 1, when the two numbers are relatively prime. So let's go ahead and prove that, because if we know that we only care about when the numbers are relatively prime, then that means we have much less experimental work to do, which we'll see in a moment. So I claim that if a to the t is congruent to 1 mod n for some t, for some power t, then the greatest common divisor of a and n must be equal to 1. So you only have to worry about when the greatest common divisor is equal to 1. And we're not going to prove it the other way, but that's also something you can do. So let's go ahead and prove it in this direction. So a to the t is congruent to 1 mod n. Well, what does that mean? Well, that's just another way of writing a to the t is equal to 1 plus kn for some k, right? Because that's exactly what it means to be congruent to 1 mod n. Well, we can rewrite this as 1 is equal to a to the t minus kn, right? So we're just subtracting kn from both sides and then just normal linear equation manipulations. And then this implies that 1 is equal to a times a to the t minus 1 minus k times n. So that's sort of a weird way of writing it, right? But we're breaking up the a to the t into a copy of a and then a copy of a to the t minus 1. But then now what you notice is that means that the 1 is a combination of a and n. But of course, if 1 is a combination of two numbers, then that means the greatest common divisor of those two numbers is equal to 1. So basically what we're saying is that a and n are relatively prime. And so why does this matter? So this matters because in the big table that we had a moment ago, so in this big table, that means that we don't need to worry about anything that's not relatively prime. So that means we don't have to worry about that row. We don't need to worry about this row, this row, this row, this row, this row, 9 or 10. So we can just cross out all those rows. We don't even have to generate them. So we don't even have to write them out because the numbers there, the A's there aren't relatively prime. And so you end up with just this table with 4 numbers, 1, 5, 7, and 11s. And so those are the only numbers that are relatively prime. And well, you notice that when you reduce it to just the rows that are relatively prime, you do end up seeing a similar pattern. So you see that there are columns that are all 1s. Let's see, let me circle them all. Which then means that in conclusion, if a squared is congruent to 1 mod 12 for a such that a is relatively prime, if your original number is relatively prime to 12, then a squared is congruent to 1 mod 12. And so because we looked at the theorem really carefully, we're able to say that we only need to do experiments for these, and then we can try to figure out what power. So in this case, a power of 2 is enough for any relatively prime thing to be equal congruent to 1. What about for all your other powers? And that's where I'm going to have you all do experiments. You guys can work together on these worksheets. You can talk to each other so you can divide and conquer. And I want you to try to pay attention to the patterns. Do you get a column of all 1s or are the 1s scattered around? Like, how does this all work? And so with that, this worksheet is also available on the website. So on the course website as the under the pre-lecture notes for today. So please, everyone, fill out the worksheet, talk to each other, try to figure out what's going on. And with that, go for it. So as in all the other times I've had you do interactives, while you're doing it, try to pay attention to any patterns that you see. And those are patterns that might end up becoming useful later on. And I should warn you that the patterns in this particular exercise are a little bit harder to figure out than some of the other patterns have been. So these patterns are a little bit trickier. also, as you have multiple tables filled in, you should start trying to see if there's some connection between the characteristics of the table, of the mod, of the number of relative primes, etc., and the point at which it starts repeating. See if there's some connection between the two. Okay, so I'm going to give you all another 3 minutes to consolidate things among yourselves. I know some of you are working in groups, and so you should share your results. As I've been saying, try to pay attention to the number of rows in the table and when things start repeating, and see if there's some pattern there. They're not always going to be the same, but maybe there's some pattern. Okay, so let's go ahead and wrap up together. So I did actually, so hopefully you guys found some patterns. I've been trying to hint at things, and yes, the patterns in this particular set of tables are a lot harder to spot than some of the patterns we've seen in some of the other tables. And yes, this is a much more complicated phenomenon. Let me turn down the lights again. Oh, no. Okay. Okay, so after you have all tables, one of the things that you might start staring at is, well, the patterns seem a lot more complicated here. There isn't some obvious number. So it's not just n-1. Like clearly it does repeat by len, but you don't know exactly when it repeats. So this will all be available online, so you don't need to worry about copying it down now. But one thing I wanted you guys to notice, and I was trying to hint at really, was you need to pay attention to when you start getting columns of ones. So you have multiple columns of ones. Here you have these columns of ones. Here you only have this one column of ones. And here you have two different columns of ones. And one thing that you might notice is that the column that corresponds to the number of relative primes always happens to be ones. Sometimes you have other columns that are also ones. But here we have a table of 8 rows, and the 8th column is also all ones. Here you have a table of 6 rows, and the 6th column is all ones. Here, 6 rows, and the 6th column is all ones. Here, 4 rows, and the 4th column. Here, it's 4 rows, the 4th column is all ones, even though you also have the 2nd column is all ones. And this pattern turns out to be really, really important. So unfortunately, sometimes these patterns are hard to spot because sometimes, occasionally, you get things messing up that pattern, like the fact that for powers mod 8, the 2nd column is also all ones by happenstance. Or like here, the 4th column is also all ones. And these sorts of things can really confuse you whenever you're trying to find patterns because there are several different things at work. But that is the basic thing that we're going to try to deduce. And so from the exercise, we want you to conjecture the different patterns. And one thing that might also help is if you include the prime modulus. So notice that a squared is congruent to 1 mod 3, a to the 4th is congruent to 1 mod 5, and so on. A to the 6 is congruent to 1 mod 7. And we also, what we figured out is a squared is congruent to 1 mod 8, a to the 4th is congruent to 1 mod 10, a to the 6 is congruent to 1 mod 14, and a to the 4 is congruent to 1 mod 15, and a to the 6 is congruent to 1 mod 18. And so one of the ways that you might have figured out this pattern that the number of relative primes happens to correspond to a column is, notice, if you're in a prime modulus, the number of relative primes is exactly p minus 1. So that was one of our results back from when we were studying relative primes. If you happen to have a prime number, the number of numbers that are smaller than and relatively prime to it is p minus 1. And so that's one of the ways that you might have guessed that it has to do with this number of relative primes, or that it has to do with the size of your table. And so with that, that is going to end the first portion of today's class, this interactive portion.